Alright, this video we're going to go over the first couple questions from the part 4 of the semester 1 review. So in this problem we're given a table, we're asked for a trapezoidal sum to approximate this definite integral. And so we just think about our area of a trapezoid. A equals, I think in class we've been doing it as b1 plus b2 over 2, the average of the bases, times the height. Of course, you can factor out that 1/2, or that 2 in the denominator, make it a 1/2. But either way, so now I just do this for each of my 3 trapezoids. And this problem is particularly nice because they actually tell you which 3 subintervals to make. Sometimes they just say make 3, but this is nice. So we go from 2 to 5, from 5 to 7, from 7 to 8. So we know these are my B1 and B2 for my first trapezoid. So let's write that out. So it's going to be 10 plus 30 over 2. And then the height of this trapezoid is going to be 3 because we're going from 2 to 5. Then the same thing for the next one. Let's add up all these trapezoids. 30 plus 40 over 2, average of the bases, times the height. This time is 2 from 5 to 7, plus 40 plus 20 divided by 2. This time the height is 1 from 7 to 8. And then simplify, add all that up, and I believe you get 160. All right, next problem. Which of the following is the midpoint Riemann sum for this definite integral using 4 subintervals of equal length or equal width? For a problem like this, I almost always want to start with the width of each subinterval. So I'm going to have 4 subintervals, and my overall interval is from 6 to 4. That means my delta x, my width, is going to be 1/2, and we can see that the formula for delta x is b minus a over n, where b and a are the endpoints of the overall interval, and n is the number of subintervals. So in this case, that's going to be 6 minus 4 over 4, which is 1/2. So it's 1/2 that's the width of each of our rectangles, and we can factor that out. And in this case, we do see they did factor out the widths, and it should be 1/2, not 1/4. So any of the ones with a 1/4 can be crossed out immediately. Now I'm looking for the inside, and I'm looking at, okay, which ones make sense for the midpoint. And in this case, it's actually fairly easy because we can see that there's only 2 options left, and this one is a trapezoid. So I can just see from the format there that that's a trapezoid. But because this is a review, let's think about it a little bit more in depth, how I would usually do this with a midpoint. I would think about, okay, whatever my graph looks like, I'm not actually concerned about that. I'm just concerned with what are the numbers I'm going to be plugging in. So here's 4, here's 6. And if I cut that into 4 subintervals, here's 5, here's 4.5, 5.5. So those would be my subintervals, my actual rectangles with a width of 1/2. But because we're using a midpoint, we're not going to use the left endpoint to get the height. We're not going to use the right endpoint to get the height. We're going to use the midpoint, go up from there, plug in the midpoint as the x value to the function to get the height. So what I'll actually end up plugging in is this midpoint of 4.25, this midpoint of 4.75, midpoint 5.25, midpoint of 5.75. So those are the x values that I would plug into the function to get the height of each of my rectangles. And so I can see in this last one, I've plugged in a 4.25, my first midpoint, to the function to get my height. You know, if we're concerned for time and we just do a quick process of elimination and say that's the only one that makes any sense, sometimes we have to leave it there, but sometimes it is good to just double check, make sure you didn't overlook anything, and actually make sure, okay, I'm pretty sure this is the only reasonable choice, but let me just go through it anyway. And again, we're also reviewing here, so nice to review the whole midpoint idea. Moving on. So we're approximating this definite integral again, but now we're doing it with a left Riemann sum, a right Riemann sum, and a trapezoidal sum, each with 4 subintervals of equal width. And basically we're asked to put these things in order. Which one of our sums is going to be smallest, biggest, in the middle, and then compare that to the actual definite integral. And so we just need to think about this graph, and so, or super rough graph, but it's going to look roughly like that. And so I see two things. I see that this is increasing, and I see that it's concave down. And I know that those are the things that tell me whether or not we have an overestimate or an underestimate, depending on the method of approximation. So because it's increasing, my left endpoint will be an underestimate. Draw any particular left endpoint rectangle here, and your missing area. Because it's increasing, then also my right endpoint will be an overestimate. Again, draw some arbitrary right endpoint rectangle, and I can see that it's over. And then the fact that it's concave down tells me that my trapezoids will also be under. Trapezoids can be a little harder to see. I like to draw sort of a huge trapezoid because it's easier to see. Different color here. So let's say we've got a trapezoid here. Under. And so I have two underestimates, one overestimate, and then obviously the function value. So the question that remains is to compare my two underestimates. Basically, I know it's either this one or this one, because the right endpoint has to be the biggest one. It's my only overestimate. And then it's just a matter of both the L and the T. Well, actually, yeah, both the L and the T are both underestimates, so it really actually has to be just this one here. For a second, I was thinking that the L and the T were the ones that were being switched, but no, they were nice to you there. We do know that the T is greater than the L. We know this. My trapezoidal approximation is going to be closer to the actual answer than the left endpoint one will be. I mean, if you draw trapezoids with equal width, you can see that pretty with equal to the actual rectangles. I can see, okay, yeah, that's much closer than the left endpoint one. All right, moving on. So now no more estimation, actually evaluating an integral. We don't know a quotient rule, so we have to simplify this first. You can either think about dividing the x squared into each term in the top, or bringing it into the numerator as an x to the negative second and then distributing it. But either way, you're going to get the indefinite integral of x plus 5x to the negative second dx. Take the antiderivative of each term individually, add 1 to the exponent, and then divide by that new number. So 1/2 x squared plus add 1, that's going to be -1, divide by that, that's going to turn this negative 5x to the negative first, and then always a plus c. that is this one. Back to area here. So in this case, they don't say anything about approximating. And then they give us this very strange graph, and they ask us about the absolute value. So a couple things are happening here. One, I don't have an actual equation, so I can't do this by taking an integral and plugging things in, doing antiderivatives. So the only option really is to use areas. And so we spent a day in class early in chapter 5 talking about how we could use area and just kind of split things up into geometric shapes that we can find the area of. For example, this trapezoid, or this chunk here, is really a trapezoid. So it has area of 1/2 base 1 plus base 2 times the height, using the other version of that formula from what we did in the first problem. My base 1 is 1, my base 2 is 2, my height is 1. Here's base 1, base 2, height. Then we can do the same thing with the next chunk. This is a triangle. So it's 1/2 base times height, which are both 1. That's just 1/2. Didn't simplify that one, sorry, that one was 3/2. And then we have another triangle here. And that one is also 1/2, the base is 1, but this time the height is -1, which would give me an area of -1/2. But, other little wrinkle in this one, they put an absolute value around this function. What does that absolute value do? Well, all it does is it takes anything that's negative and flips it over, right? We'll call that a triangle. And so that triangle that was an area of -1/2 is actually an area of +1/2. So then I add it all up and I get 5/2. Another definite integral here, no area to really think about. And once again, I need to simplify this. I don't have a product rule, so I've got to simplify. This becomes x to the 3/2 plus x to the 1/2. That 3/2, of course, is coming from, this is x to the first, this is x to the 1/2. Multiply them together, and you add the exponents. So then that's 2/5 x to the 5/2, doing your antiderivative power rule, plus 2/3 x to the 3/2. Plug in 0 and 1 and subtract. I'm going to get 2/5 plus 2/3 minus 0. And when you do your common denominator and combine those, you get 16/15. All right. I think that's the last one we have, right? Yep. Okay, that is all for this.